In this video, we'll discuss a case of a pendulum, which is the horizontal elastic pendulum with a free and damped oscillation. The horizontal elastic pendulum is a mass connected to one end of the spring that goes back and forth horizontally. The mechanical energy is equal to the kinetic energy plus the elastic potential energy plus the gravitational potential energy, where the GPE is equal to 0. So we left up with mechanical energy at time t is equal to the kinetic energy plus elastic potential energy. At maximum elongation, V is equal to 0, so the kinetic energy is equal to 0. Thus, EPE is equal to the mechanical energy, which is at its maximum. The same thing regarding the maximum compression. However, at the origin O, it has the EPE to be 0, where the kinetic energy is at its maximum equals to the mechanical energy. In order to study how the position of the mass m changes over time, we need an equation. Just keep in mind that the initial conditions are always given in the question. I mean by the initial conditions, the x0 and the v0, the initial displacement and speed. The time equation that can help us study the behavior of the block at any time t can be derived in two ways, either using the Newton's second law or the conservation law of mechanical energy. We know that the sum of the external forces is equal to ma. Projecting along the direction of motion, we get minus t equals to ma. It is minus t negative since it is opposite to the direction of motion during elongation, where t is equal to kx. K is the stiffness constant. We divide by m and we get an equation of second order, x double prime plus k over m, x equals to 0. Another method is using the law of conservation of mechanical energy, where its derivative is equal to 0. The mechanical energy at any time t is equal to the kinetic energy plus EPE, neglecting the GPE as we take it as at reference. So the derivative is equal to mvv prime plus kx prime x equals to 0. Taking v as a common factor, it is always different from 0 since it is in motion. So we left up with x double prime plus k over mx equals to 0, the second order differential equation. However, in order to solve this equation, we don't need it in the differential form, meaning that we want to get rid of the double prime. We need it as a function of time t as x equals to t. It is not required to know how to solve it. You just have to know from where it comes. The question gives you the solution, which could be one of these two, either a cosine function or a sine function, having three unknowns to be determined: the xm, omega, which is the proper angular frequency, and the phase difference. These three unknowns are the characteristics of this oscillation. So the new goal is to find the value of these three. In order to find the proper angular frequency, you can just compare the second differential order equation you obtained, which is x double prime plus k over m x equals to 0, to that of the simple harmonic equation. By comparison, you can deduce that the proper angular frequency is equal to the square root of k over m, where k is the stiffness constant. Keep in mind that the proper angular frequency is also equal to 2 pi over the proper period, or equals to 2 pi times the proper frequency. So that you can deduce the proper period equals to 2 pi square root of m over k, and the proper frequency 2 pi the square root of k over m, since they are inverse. Another thing you have to find is the maximum displacement, which is always positive. There are two methods, either using the conservation law of mechanical energy at t0 and at x maximum, or using the fundamental trigonometric relation sine squared phi plus cosine squared phi equals to 1. The first method, using the conservation of mechanical energy. The mechanical energy at t0 equals to the mechanical energy at x max, where EPE plus kinetic energy at O is equal to the EPE maximum. So you add the equations and divide by the stiffness constant K, you get x maximum squared equals to x0 squared plus m over K, which is the inverse of the omega squared, times v0 squared. So we can deduce that the x maximum is equal to the square root of x0 squared plus v0 squared over omega 0 squared. Keep in mind that x0 and v0 are always given. These are the initial conditions. Another method is using the fundamental trigonometric relation sine squared phi plus cosine squared phi equals to 1. We find it at t equals to 0 in terms of x0 and v0. For example, the given solution for the second differential equation is a sine function x equal to x max sine omega t plus phi. At t0, the x0 is equal to x maximum sine phi. We need also to find v0, which is the derivative of x0, which gives us omega 0 x max cosine phi. So, here we can find sine phi and cosine phi in terms of x0 and v0 and square them, then add them, solve it equal to 1. So we get x max. The last thing you have to find is the phase difference phi. However, there are 4 possible phase differences and one is correct. The valid phi depends on the sign of both cosine phi and sine phi at t0. For example, the solution for the second order differential equation is a cosine function, x equals xm cosine omega t plus phase difference. In order to find the phi, you need to solve it at t equals to 0, where x0 is equal to x max cosine phi. So cosine phi is equal to x0 over x max, where x max is always positive. So cosine phi depends on the sign of x0. In order to find psi, you need the derivative. So v0 is the derivative of x0, which gives you minus omega 0 xm sine phi, where sine phi is equal to minus v0 over omega 0 x max. Knowing that omega 0 x max is always positive, so sine phi depends on the sign of minus v0. Thus, the cosine depends on the sign of x0 and sine depends on the sign of v0, and vice versa in case of if the solution proposed is a sine function instead of cosine. Thus, if x0 is positive and v0 negative, then cosine and sine are both positive, then phi is in quadrant 1. However, if both x0 and v0 are negative, then cosine is negative and sine is positive, then the phase difference is in quadrant 2. If x0 is negative and v0 is positive, then cosine and sine are both negative. Phi belongs to quadrant 3. And if both x0 and v0 are positive, then cosine is positive and sine is negative, then phi belongs to quadrant 4. That's everything for today, and here is a summary sheet for all the rules and how to find the unknowns.